So, I am going to explain about the basics of coordination compounds. And now, coordination compounds, they are made by reaction between two simple salts, two simple or single salts in a proper ratio, and there is formation of coordination compound or complex compound. कोऑर्डिनेशन कंपाउंड या कॉम्प्लेक्स कंपाउंड बनता है. जैसे दिस कॉपर सल्फेट प्लस ammonium hydroxide, or you take ammonia liquor, mother liquor. So reaction, this is salt, this is also salt. As a result, there is this is the conformity test for copper. To the solution, we add ammonium hydroxide or ammonium. There is solution of this complex. This is deep blue color complex. Deep blue color complex is formed, and this is coordinate compound, this is complex compound. Now, coordinate compounds have a very special point that there is the central metal atom, and by here there is copper, and the three NH3 attached, they are held together by coordinate bonds. They are held together by coordinate bonds. And this is ligand, amine. This is not ammonia, this is amine, and it is called ligand. This is amine. It is ligand. This copper is central metal ion, central metal atom, and this square bracket, it is coordination sphere. And coordination sphere has some charge, like this. Here we have sulfate, so there is SO4, 2 minus. Now this ion, this is an ion outside the coordination sphere. It is called as counter. It is called as counter anion. It is called as counter anion. And it is called as the central metal and the ligands. It is called as complex. It is called as complex ion. So here it is complex cation. It is complex cation. So the complex can be anionic or cationic. Similarly, counter ion can be anionic or cationic. So both the ways are possible. Like say, other example here, for FeCN6. This here, FeCN6, it is complex anion. This potassium, it is counter. It is counter cation. So there can be variation in both the ways. Now I am going to explain very important part in coordination compounds. Warner's theory of coordination compounds. So Alfred Warner proposed the theory and was the first person to explain how coordinate compounds are formed. And there are some guidelines which are very much important. And first point is every metal has two types of valences. Two types of valences. Valences of two types. Primary and secondary. Valences are of two types, primary valency and secondary valency. Now, second point, primary valencies are satisfied by negative ions and are variable and it is equal to oxidation number. You have to keep in mind variable and it is equal to oxidation number. This is primary valency. So oxidation number is what? Primary valency. Secondary valencies are satisfied. Secondary valencies are satisfied by ligands. Ligands are the specialized particles like ions or molecules. Ligands are neutral in nature, or it can be anionic or it can be cationic. So ligands are specific, capable of providing electron pair to central metal atom. They are capable of providing electron pair to central metal atom. They are the ligands. So the secondary valencies are always fixed. Secondary valencies are always fixed for a metal. Always fixed for metal and is non-ionizable. It is non-ionizable and it is equal to what? It is equal to coordination number. It is equal to coordination number. So the number of ions surrounding the central metal atom, it is equal to coordination number. So this is the second point. Now third point, secondary valencies are responsible for providing responsible for providing particular shape. They are responsible for providing particular shape to the molecule. It means they are directed, they are projected in a particular direction. The coordinate compounds have different structures, that they can have octahedral structure or they can have the square planar, depending on the type of molecule. So these are very key points of the coordinate compounds, and many things are explained. And so this is about the Werner's theory. Now see some important points. So in this first is coordination number. So coordination number is the number of ligands attached to the central metal atom, or it is equal to the what? Secondary valency. So it is the number of ligands surrounding central metal atom. Number of ligands surrounding the central metal atom, and it is always fixed, as you know. It is always fixed. It is always fixed for a metal. It is always fixed for a metal. Like just the previous example, here we take so here the 6 CN ligands are attached, and so we say the coordination number of Fe is equal to 6. 6 ligands are attached. So this is coordination number. Now second point is the ligands. So as you know, ligands are species. They can be molecules or they can be ions. So species capable of providing electron pair to central metal atom. They provide electron pair to central metal atom. So ligands are the species capable of providing electron pair to central metal atom. And so ligands are of 3 types. Neutral, then negative and positive. Neutral, negative and positive. So as neutral means they have no charge. Neutral have no charge. Like NH3, amine. Then CO. This is not carbon monoxide, this is carbon ion. Ligands have their specific names. Then H2O, this is aqua. Water is aqua. Water is also liquid, you know. Water has lone pair, like this, you know this thing. Similarly here also, so we have this. Then negative ligands, so all the anions, so they have negative charge. And example, all the anions. But we do not name like chloride, bromide, iodide or sulfate. Like SO4 is called as sulfato. Chloride is called as chlorido, iodo, bromo, like this. Nitrite, nitrato, nitrite, nitrato. So like this. Similarly, positive means they have positive charge. They have positive charge, like this. NO plus, nitrosyl. There are very few. Positive are very few, but mostly neutral and the negative. So there are the negatives. And suppose you take this Fe. Fe has the octahedral geometry, and this Cn and this Cn. So these all five are in one plane, and here this Cn is at the one is at the top, other is at the bottom, and there is the formation of octahedral complex. This is octahedral. This is octahedral molecule. So this is about the ligands. Ligands can be of different type, and they are all simple ligands. So ligands can be very complex also. You have seen the ligand depending on charge, neutral, negative and positive. Now the ligand other classification depending on their ability to bond with number of points or places. Number of points or places to central metal atom. Number of points, because the ligands have bonding sites. Ligands can attach only to the bonding site to the central metal atom. Now, in this first is monodentate ligands, having only one binding site, only one binding site, like chlorido, bromo, iodo, cyano, they or nitrito, they all are monodentate. Only one bonding site. This etc. Many more. They are monodentate. Then second, didentate. They have two bonding sites. They have two bonding or binding sites. Two binding or two bonding sites. Like this. This is oxalate, but we call oxalato. Oxalato. So it has two bonding sites. Oxalato. Similarly, other is this is also bidentate. It is ethylene diamine. So it is didentate ligand. Now, third is dent. Third is ambident or ambidentate. Ambidentate ligand. So ambidentate ligands are the ligands having two bonding sites, but only one is active at a time. Two bonding sites, but only one is active at a particular time. Two bonding sites, but only one is active. Only one is active at a time. Only one is active at a time. Like Cl and its opposite NC. Then NO2 and ONO. So here it is nitrito. This is called as nitrito. It is called if it is bonding towards O from O side. So it is called as O nitrito. This is simple nitrito. This is cyano. This is isocyano. So this is ambident or ambidentate ligand. Now next is polydentate ligand. Polydentate ligand. Polydentate ligand. So when the ligands have more than two bonding sites, there are more than two bonding sites. We do not say tri or tetra, but after two we follow. It is more than two bonding sites. And EDTA ion, ethylene, diamine, tetra, acetate ion, ethylene, diamine, tetraacetate ion. So similarly, this ethylene, this ethylene and diamine tetraacetate. So here we have N and this CH3 CH. Here there will be CH2. Here there will be CH2. Count the, because carbon has 4 valency. So here these things have to be taken. Now see the bonding site, number of bonding sites. This is 1, 2, 3, 4, 5 and 6. So it is hexadentate ligand. This is hexadentate ligand. Now next is denticity. So denticity means the ability of a ligand, to attach to central metal atoms by a fixed number of sites. So denticity relates to that number of bonding sites a molecule has or ion has. So what we can say, if you take monodentate, so the denticity is said to be 1. If it is bidentate or didentate, denticity is 2. Is that clear? So this denticity. Next is chelate. So chelate is the a special type of ligands which forms a ring. When a ligand forms ring with central metal atom, there is formation of ring. Ring is formed. So naturally you have to keep in mind that at least it should be didentate and polydentate. You have to keep in mind. Example, didentate and polydentate ligands. They form the ring. Like oscillator. Here if we have M metal, and so here we write OX. Here let it be NS3. Here there can be NS3. So here there is, we can write any complex as per our convenience. For any example is not mentioned, write simply here n plus, or it can be minus depending on the charge. So this is very important point about the quadrature compounds.